For most of modern cosmology, the universe was thought to be vast but orderly. Galaxies form clusters, clusters form superclusters, and beyond a certain scale, matter should smooth out into uniformity. This assumption sits at the foundation of how we understand the cosmos. But the universe doesn't fully cooperate. As astronomers began mapping distant cosmic events, something unexpected appeared. Patterns where randomness should dominate, structures spanning distances far larger than theory allows. At first, it was easy to dismiss. Too little data, too much coincidence. But as observations accumulated, the pattern refused to disappear. What emerged was not a galaxy, or a cluster, or even a supercluster. It was something far larger. The Hercules Borealis Great Wall, a structure stretching across billions of light years, large enough to challenge the idea that the universe ever truly becomes uniform. If structures like this exist, then our models of cosmic evolution may be incomplete. The universe may be more structured and more extreme than we expected. And if humanity exists within such a colossal formation, our place in the cosmos isn't just small, it's almost invisible. Before we go any further, if you enjoy calm explorations of how the universe behaves on its largest scales, a like or subscribe helps support this work, because the Great Wall isn't just a curiosity, it's a warning that the universe may be far stranger than our theories. To understand why the Hercules Borealis Great Wall is so disturbing, we first need to understand what cosmologists expected the universe to look like. On small scales, matter in the universe is highly structured. Stars gather into galaxies, galaxies gather into clusters, and clusters connect through vast filaments of matter that stretch across millions of light years. Between these filaments lie enormous voids, regions where almost nothing exists. This network of matter is known as the cosmic web. Yet, according to modern cosmology, this structure should not continue indefinitely. When viewed across sufficiently large distances, the universe is expected to become statistically uniform. This idea, known as the cosmological principle, suggests that while matter can cluster locally, it should not form coherent structures beyond a certain scale. On the largest scales, the universe should appear smooth, almost featureless, with no preferred directions or colossal patterns. This assumption is not arbitrary. It is built into our most successful models of cosmic evolution. Simulations of the universe's growth from the Big Bang show that gravity can create galaxies, clusters, and filaments, but only up to a limit. Beyond that limit, randomness should dominate. Structure should dissolve into statistical noise. For decades, observations seem to confirm this picture. Large galaxy surveys revealed immense structures, but none appeared to violate the fundamental expectation of cosmic uniformity. The universe looked vast, complex, and hierarchical, yet ultimately bounded by an invisible ceiling of scale. There was an implicit understanding that while the cosmos could be enormous, it could not be arbitrarily structured. Then astronomers began to notice something that did not fit this expectation. Unlike galaxies or clusters, the Hercules Borealis Great Wall was not discovered through traditional galaxy surveys. Instead, it emerged from the study of gamma-ray bursts, brief, extremely powerful flashes of radiation produced by distant cosmic catastrophes such as collapsing stars or merging neutron stars. Because gamma-ray bursts can be detected across enormous distances, they act as markers of the farthest reaches of the universe. When scientists mapped the distribution of these bursts across the sky, they expected to see randomness. Gamma-ray bursts should appear scattered across space, reflecting the large-scale uniformity predicted by cosmology. But as the data accumulated, a strange pattern began to appear. Certain regions of the sky contained an unusually high concentration of gamma-ray bursts. At first, this seemed like a coincidence. The data set was limited and statistical anomalies are inevitable in large-scale surveys, but as more bursts were detected and their distances measured, the clustering became harder to ignore. The pattern suggested that many of these events were occurring within a single enormous region of space. If interpreted literally, the data implied the existence of a structure spanning billions of light years, the Hercules Corona Borealis Great Wall. The name itself reflects its staggering scale. This was not a cluster of galaxies or even a supercluster. It was something far larger, a vast region of enhanced matter distribution stretching across a significant fraction of the observable universe. Its estimated size dwarfed most known cosmic structures, approaching dimensions that seemed incompatible with the cosmological principle. The reaction within the scientific community was cautious, even skeptical. Some researchers argued that the structure might be an artifact of limited data or observational bias. Others suggested that gamma-ray bursts might not trace matter distribution reliably enough to justify such conclusions. Yet the possibility remained. If the Great Wall was real, then the universe was violating one of its most fundamental assumptions. And that possibility was deeply unsettling. The true impact of the Hercules Corona Borealis Great Wall becomes clear only when we attempt to comprehend its size. The Milky Way galaxy, which feels unimaginably vast on human scales, spans roughly 100,000 light-years. The local group of galaxies extends a few million light-years. Even massive superclusters typically measure a few hundred million light-years across. The Great Wall, by contrast, is estimated to span more than 10 billion light-years. At that scale, comparisons begin to lose meaning. The structure is so large that light itself takes a significant fraction of the universe's age to traverse it. It stretches across distances comparable to the largest observable patterns in the cosmos, occupying a portion of space so vast that it challenges our ability to visualize it. If such a structure exists, it is not merely large, it is cosmologically problematic. According to standard models of the universe, structures of this magnitude should not form. The initial fluctuations in the early universe, amplified by gravity over billions of years, are not expected to produce coherent patterns on such scales. Randomness should dominate long before any structure reaches these dimensions. Yet the Great Wall appears to do exactly that. It suggests that matter in the universe may be organized on scales far larger than theory predicts, and that the cosmic web may extend into regimes where our models cease to apply. If true, the Great Wall is not just an outlier. It is a sign that our understanding of cosmic structure is incomplete. And if humanity exists within a universe shaped by such colossal patterns, then our position in the cosmos is not just small. It is embedded within structures so vast that they redefine what it means to inhabit the universe at all. If the Hercules Corona Borealis Great Wall is real, then it represents more than just an unusually large cosmic structure. It represents a direct challenge to one of the most fundamental assumptions in cosmology, that the universe becomes uniform on the largest scales. Modern cosmology is built on the idea that while matter can cluster locally, it should not form coherent patterns beyond a certain size. This expectation arises from the conditions of the early universe. After the Big Bang, matter was distributed with only tiny fluctuations in density. Over billions of years, gravity amplified these fluctuations, forming galaxies, clusters, and filaments. But gravity has limits. It cannot coordinate matter across arbitrarily large distances within the finite age of the universe. In simple terms, there has not been enough time for gravity to build structures spanning billions of light years. Simulations based on the standard cosmological model reflect this constraint. They produce vast cosmic webs filled with filaments and voids, but they do not generate single, coherent structures on the scale suggested by the Great Wall. When such enormous patterns appear in data, they are usually interpreted as statistical coincidences rather than physical objects. This is what makes the Great Wall so unsettling. If it is a genuine structure rather than a statistical illusion, then either our understanding of cosmic structure formation is incomplete, or the assumptions underlying the cosmological principle are not entirely accurate. The universe would not merely be vast and random on large scales. It would be organized in ways that exceed theoretical limits. In that case, the Great Wall is not just an anomaly. It is evidence that the universe may be capable of producing patterns far larger than we believed possible. Faced with the implications of the Hercules Corona Borealis Great Wall, scientists have proposed several explanations. None of them fully resolves the mystery, and each raises new questions about the nature of cosmic structure. One possibility is that the Great Wall is a statistical artifact. Gamma-ray bursts are rare events, and their distribution across space is uneven. With limited data, random clustering can sometimes mimic large-scale structure. In this view, the Great Wall is not a physical object, but an illusion created by small sample sizes and observational bias. Another possibility is that gamma-ray bursts are not reliable traces of matter distribution. Unlike galaxies, which directly map the cosmic web, gamma-ray bursts occur in specific types of environments and may be influenced by factors unrelated to large-scale structure. If their distribution is biased, then apparent clustering may not reflect genuine cosmic patterns. A more radical explanation is that the Great Wall represents a different kind of structure altogether. Rather than a single coherent object, it may be a loose alignment of filaments and clusters that appear connected only from our perspective. At extreme distances, projection effects can transform separate structures into seemingly unified patterns. Yet even these explanations do not fully eliminate the tension. If the Great Wall is partly real, partly illusory, then the universe may be more structured than our models predict, but in ways that are difficult to classify. The boundary between structure and randomness becomes blurred, and the distinction between physical reality and statistical pattern becomes harder to define. The Great Wall, in this sense, is not just a cosmic object. It is a test of how we interpret the universe. To understand why structures like the Hercules Corona Borealis Great Wall are so difficult to interpret, we must confront a deeper issue. We do not observe the universe directly. We reconstruct it from fragments of light, signals, and rare events scattered across immense distances and timescales. Our maps of the cosmos are incomplete. Galaxy surveys cover only certain regions of the sky and only certain ranges of distance. Even the most ambitious projects observe only a fraction of all galaxies. Beyond a certain point, galaxies become too faint to detect, and our picture of cosmic structure becomes increasingly speculative. Gamma-ray bursts, which revealed the Great Wall, are even more indirect. They are rare, transient events that occur unpredictably across space and time. Using them as markers of large-scale structure is like trying to map a city by observing only occasional flashes of lightning. Patterns may emerge, but they are difficult to interpret with certainty. Moreover, the universe itself imposes limits on what we can observe. Light takes time to travel across space, meaning that we see distant regions as they existed billions of years ago. Cosmic expansion stretches and dims signals, erasing information about the farthest structures. Beyond the cosmic horizon, entire regions of the universe are permanently inaccessible. In this context, the Great Wall exists at the edge of what we can meaningfully observe. It occupies a region of space where data is sparse, uncertainty is high, and interpretation becomes fragile. The question is not only whether the Great Wall is real, but whether our methods are capable of distinguishing reality from pattern at such scales. If our maps are incomplete, then our understanding of cosmic structure is incomplete as well. And if structures like the Great Wall exist beyond the limits of our observational reach, then the universe may be far more complex than any map we can draw. When we think about our position in the universe, we usually imagine familiar scales. Earth orbits the Sun. The Sun lies within the Milky Way. The Milky Way belongs to a small group of galaxies bound together by gravity. Beyond that, we picture vast emptiness punctuated by distant clusters and filaments. But if the Hercules Corona Borealis Great Wall is real, this picture is incomplete. It suggests that our cosmic neighborhood is embedded within a structure so large that it dwarfs every scale we normally use to understand the universe. The Milky Way, with its hundreds of billions of stars, becomes a microscopic feature within a filament. That filament becomes a thin thread within a wall that stretches across billions of light years. The structures that once seemed unimaginably vast are reduced to faint patterns within something far larger. At this scale, distance loses its intuitive meaning. The Great Wall is not something we could ever perceive directly. It is not a visible object in the sky. It is a statistical pattern inferred from the distribution of distant events and galaxies. Yet its implications are tangible. If humanity exists within such a colossal structure, then our position in the universe is not merely small, it is deeply embedded within patterns we can barely detect. This realization changes how we interpret cosmic geography. We are not isolated observers looking out at a random universe. We are inhabitants of a vast structural system whose boundaries we cannot see and whose full extent we cannot comprehend. The night sky, which appears scattered and chaotic, may actually be part of a coherent architecture that spans a significant fraction of the observable cosmos. In that sense, the Great Wall is not just an astronomical curiosity, it is a reminder that our intuitive sense of scale may be profoundly misleading. If structures like the Hercules Borealis Great Wall truly exist, then they force cosmologists to reconsider some of the most basic assumptions about the universe. The cosmological principle, the idea that the universe is homogeneous and isotropic on the largest scales, has been a cornerstone of modern cosmology. It underlies models of cosmic expansion, inflation, and the distribution of matter. The Great Wall appears to challenge this principle. If matter can organize itself into structures spanning billions of light years, then the transition from structure to uniformity may occur at scales far larger than previously believed. This does not necessarily invalidate the cosmological principle, but it suggests that its domain of applicability may be more limited than assumed. The implications extend beyond structure formation. Models of cosmic inflation, which describe the rapid expansion of space in the early universe, predict specific patterns of density fluctuations. These fluctuations seed the formation of galaxies and clusters, but they are not expected to produce coherent structures on the scale suggested by the Great Wall. If such structures exist, they may indicate that inflationary physics is more complex than current models suggest. Dark matter and dark energy may also play a role. The distribution of matter on the largest scales is influenced by the interplay between gravitational attraction and cosmic expansion. If the Great Wall reflects genuine matter clustering, it could imply that dark matter interacts in unexpected ways or that dark energy influences structure formation more subtly than previously thought. In this sense, the Great Wall is not just a large object, it is a stress test for cosmology. If our theories can accommodate it, they must become more nuanced. If they cannot, they must be revised. Either outcome forces us to confront the possibility that our current understanding of the universe is incomplete. One of the most unsettling implications of the Hercules Borealis Great Wall is the possibility that the universe has no true upper limit to structure size. If one structure can span billions of light years, then what prevents even larger patterns from existing beyond the limits of our observation? Other enormous structures already hint at this possibility. The Sloan Great Wall, the giant quasar groups, and other large-scale features stretch across hundreds of millions or even billions of light years. Each discovery has pushed the perceived boundary of cosmic structure outward. The Great Wall may simply be the most extreme example we have encountered so far. If this trend continues, then the universe may not transition cleanly from structure to uniformity. Instead, it may contain patterns at every scale, from the smallest fluctuations to the largest conceivable formations. The cosmic web may not dissolve into randomness at large distances, but evolve into increasingly complex architectures. This raises a profound question. Is the universe fundamentally uniform, or is uniformity merely an approximation that breaks down at extreme scales? If scale has no true limit, then our cosmological models are not describing a finished picture of reality. but a simplified version that holds only within certain boundaries. Beyond those boundaries, the universe may behave in ways that our current theories cannot easily capture. In that case, the Great Wall is not an anomaly. It is a glimpse of a deeper structure we have only begun to perceive. And if the universe contains patterns larger than anything we can observe, then our position within it becomes even more precarious. We are not just small within the cosmos, we are embedded within structures whose full extent may forever remain beyond our understanding. The Hercules Borealis Great Wall may not be the largest structure that exists. It may simply be the largest structure we are currently capable of seeing. When the universe is viewed across different scales, a strange pattern begins to emerge. At the smallest levels, matter organizes into atoms and molecules. At larger scales, stars form galaxies. Galaxies assemble into clusters, and clusters connect through filaments that stretch across cosmic distances. Each layer of structure seems to repeat the same logic. Matter gathers, organizes, and forms patterns that are larger than the ones before. The Hercules Borealis Great Wall pushes this pattern to an extreme. If such a structure exists, it suggests that the universe may be layered with organization at scales far beyond what we previously imagined. The cosmos may not transition cleanly from structure to uniformity, but instead continue generating patterns at increasingly larger levels. In this view, the universe resembles a fractal system, where complexity persists no matter how far outward we look. This idea is unsettling because it blurs the boundary between order and randomness. If structure exists at every scale, then the concept of a largest structure loses meaning. The universe would not be bounded by a definitive scale of organization, but by our ability to observe it. Each time we extend our observational reach, we might discover new layers of cosmic architecture, each one dwarfing the last. In such a universe, our models of cosmic evolution become provisional rather than definitive. They describe what we can currently observe, not the full scope of reality. The Great Wall becomes not an exception, but a sign that the universe's complexity may be fundamentally unbounded. The Hercules Borealis Great Wall forces us to confront not only the limits of cosmology, but the limits of human perception. Our understanding of the universe is shaped by instruments, theories, and statistical methods that evolved within a narrow band of cosmic scales. We are adapted to comprehend planets, stars, and galaxies, but not structures that span billions of light years. At such scales, intuition fails. Distances become abstract, numbers lose meaning, and visualization becomes impossible. The Great Wall cannot be seen directly, only inferred from subtle patterns in distant data. It exists at the edge of what we can measure, where certainty fades and interpretation becomes fragile. This raises a deeper question. How much of the universe is truly accessible to human understanding? If the cosmos contains structures far larger than anything we can observe, then our theories may always lag behind reality. We may be mapping only a thin slice of a much deeper cosmic architecture, mistaking partial patterns for complete explanations. In this sense, the Great Wall is not just a discovery. It is a reminder that our view of the universe is filtered through profound limitations. We do not see reality directly. We reconstruct it from fragments of light and statistical traces. At the largest scales, the universe may not only exceed our expectations, it may exceed our capacity to comprehend it. The Hercules Borealis Great Wall stands at the boundary between what cosmology predicts and what observation suggests. It may be a statistical anomaly, a projection effect, or a genuine structure that challenges fundamental assumptions about the universe. But regardless of its ultimate nature, its significance lies not in what it proves, but in what it reveals. The universe does not always behave the way we expect. For decades, cosmology has relied on the assumption that the universe becomes uniform on the largest scales. This assumption has guided our understanding of cosmic evolution, structure formation, and the nature of space itself. The Great Wall, however, hints that this assumption may be an approximation rather than a law. If the universe can generate structures of such magnitude, then our theories must adapt to a reality that is more complex than previously imagined. The cosmos may not be a smooth, evenly distributed system, but a hierarchy of patterns extending far beyond the scales we can currently observe. In that case, humanity's place in the universe becomes even more precarious. We are not just small within the cosmos, we are embedded within structures whose full extent we may never fully map, understand, or even detect. The galaxies we observe, the cosmic web we map, and the structures we classify may represent only the visible surface of a far deeper architecture. The Hercules Borealis Great Wall is not simply a wall of galaxies. It is a signal that the universe may be larger, more structured, and more mysterious than our models allow. A reminder that every time we believe we have reached the limits of cosmic scale, the universe reveals something even larger. And if the cosmos continues to defy its own rules, then the greatest discovery may not be any single structure. It may be the realization that the universe is not constrained by the boundaries we impose on it.